The topic of my talk is application of the full Bayesian significance test to model selection under informative sampling. And this is a joint work with Professor Giulio Stern. In this research, we consider the problem of informative sampling, and we propose a method to identify or to select the model which describes the sample selection mechanism. We use the Bayesian approach and apply the full Bayesian significance test. Now let's give a brief description of the problem of informative sampling. Generally, in order to evaluate characteristics of the population, for example, distribution holding in the whole population, we usually draw a sample from this population. In many surveys, a sample is selected using a simple random sampling mechanism. In this case, the population model coincides with the sample model, and inference about the whole population based on the sample drawn utilizing the simple random sampling doesn't require advanced statistical method of analyzing. If sample selection process employs a more complex sampling mechanism, the population model may not coincide with the sample model. In this article, we consider the situations where the inclusion probabilities are proportional to some design variable which is associated with the outcome variable. Let's see what this means. For example, in business surveys, inclusion probabilities of sample units, which are companies in this case, are often proportional to company size measured by the number of employees. Therefore, if the outcome variable is business income, which is positively correlated with the company size, this type of sample selection is informative in the sense that the large companies with high income might be overrepresented in the sample, while the companies with smaller income might be underrepresented. In this case, we use the design variable is company size. The outcome variable is business income, and the design variable company size is correlated with the business income. This is the example of informative sampling, and in this case, if the analyst doesn't take into account the sampling mechanism, the inference about the population will be generally biased because the population model generally doesn't coincide with the sample model. This is an example. This sample selection mechanism is often referred to probabilities proportional to size sampling, and this sampling mechanism is very common in survey sampling. And in this research, we assume that the units were selected using this sampling mechanism. In our research, we discuss practical situation of public use data, where generally the only design information available to the analyst are the inclusion sample probabilities. In this case, the parametric form of the model which describes the sample selection process is not available to the analyst. In this case, this generally complicates estimation of the population model. So identifying the model which describes the sampling mechanism plays a very important role when dealing with informative sampling. Because this model is generally used in order to estimate the population model. There exist various approaches to handling informative sampling. However, they generally focus on estimation of unknown parameters, leaving the problem of model selection almost unaddressed. There are these classical inference methods, for example, maximal likelihood estimation. The other type of methods is weighting methods, which use the reciprocals of sampling frequencies. Here are some references to these methods. Implementation of the classical approach is problematic in the case of informative sampling, but as in many other applications, the problem can be solved by utilizing the Bayesian approach and MCMC. In our proposed approach, we assume that the probability of each population unit being selected into the sample is proportional to some design variable which is associated with the outcome variable, or in other words, the probability proportional to sample, probability proportional to size sampling mechanism. And we propose an approach to choose an appropriate model for the underlying sample selection process. In the proposed approach, we assume that the sample inclusion probabilities are observed. Here, I would like to emphasize that the sample inclusion probabilities are generally available in public, at least for public use files of a sample surveys. Why? Because the sample inclusion probabilities are generally defined at the stage of planning of the survey, before the stage of carrying out sampling. For example, in the survey of companies, in business surveys, the statistician generally has the list of all companies in the population, and with the localities and addresses, and he assigns the probabilities for each company to be selected into the sample. He can assign, for example, the equal probabilities to each unit, to each company. In this case, the sampling scheme is a simple random. Or he can assign the larger probabilities for the larger companies. Or, for example, he can assign larger probabilities for the companies which are situated in some specific region. Depends on the objectives of the study. So we assume that the sample inclusion probabilities are observed. We specify weighted estimation equations and show how they can be incorporated into the Bayesian paradigm. Then we impose a flat multivariate normal prior on a vector of unknown parameters. Our method allowed the application of the MCMC integration techniques. And we further apply the full Bayesian significant test, which is based on the Bayesian measure of evidence favoring the null hypothesis. One of the main advantages of the Bayesian approach is that it leads to a simple and direct technique of model identification or model selection via hypothesis testing. Here we actually eliminate the non-significant parameters from the model by carrying out the appropriate hypothesis tests. Now we'll describe briefly the full Bayesian significant tests. Let G x theta be the posterior density for theta given the data x. And let G theta be a prior probability density over the space theta, and L x theta is the likelihood. We are interested in test the hypothesis H that says that theta belongs to some subspace of theta denoted by theta H. After the data x have been observed, we use a posterior density for theta given the data for the evaluation of the E value. Let S0 denote the supremum of the posterior density under the hypothesis H, and let's define the tangential set T as all vectors of theta which belong to the general space theta, such that the value of the posterior distribution of theta given the data x is larger than S0. And then the E value or the evidence value against H is defined as a posterior probability of this tangential set. That is the integral of the posterior distribution of theta over the set T. We can approximate this integral in order to obtain the evidence value. We can approximate the integral using the posterior draws of theta, which are obtained by application the MC algorithm. The E value supporting H is 1 minus this integral. Here is how we defined this test. And now let's define the informative sampling in a more formal way. Here we have yi, which denotes the value of the outcome variable y associated with the unit I belonging to a sample S, drawn from a finite population U, and the size of the population U is large N, and the size of the sample is small n, and we define by xi and vi the vectors of auxiliary variables associated with the unit I. We assume that the population values yi are independent realizations from a population distribution Fp of yi given xi and theta. Theta is an unknown vector parameter. We also assume that the sample selection process is independent between the units, and we suppose that the probability of a unit I to be selected is pi I, and these probabilities are proportional to the values of some design variable zi, which are correlated with the outcome variable I. We assume, as I already mentioned, that pi I are known for all sampled units, which is a common situation in sample surveys. Now, application of the likelihood approach generally requires a parametric assumption on the population distribution and the model describing the sampling selection mechanism, which is represented here by the conditional expectation of the probabilities pi I given the values of the outcome variable and vector of auxiliary variables. And also, there are some parameters indexing governing this model. Now we can define the sample likelihood. It's defined here. Actually, the sample likelihood is the product of the sample densities. Here you can see that the sample densities depend on the form of on the sample selection mechanism, which is represented by the conditional expectations. Also note that if the sample selection process is not informative, where these expectations don't depend on y, then the numerator and the denominator cancel out, and the population distribution coincides with the sample distribution. However, if the sampling process depends on epsilon, the sample distribution, as you can see, doesn't generally coincide with the population distribution. Here, the expectation in the denominator actually is the integral of the product of the population density and the expectation in the denominator. Note also that the vectors of auxiliary variables may not be the same in the population and in the sample selection models. As I have already mentioned, generally the parametric form of these expectations is unknown, and our objective is to select the appropriate model for this mechanism, which will describe this mechanism. There exists common approximation for the sample selection model in the literature. The most common are the linear approximation and the exponential approximation, and these approximations can be used in the defined likelihood. However, there are a few disadvantages of these approximations. First of all, if the number of parameters indexed in the model describing the sample selection mechanism is large, estimation of unknown parameters generally leads to a very cumbersome computation process, which results in a very unstable estimate, which are not useful for the estimation purpose. Also, there are identifiability problems. In principle, one can incorporate the defined sample likelihood into Bayesian model by specifying prior distribution for the unknown model parameters, but there are also some disadvantages with this. I don't have time to explain everything which is written here, so I will just concentrate on the main results that we obtained. So I'll describe briefly the proposed approach. Here we illustrate the proposed approach for a simple model, which is a linear model, but for more complex form of the expectation, the computations are very similar. We define the estimation equations, which are very similar to the weighted regression equations. Here, jk, and then we obtain the vector j, which for a large value of n, when the sample is sufficiently large, we can use one of the version of central limit theorem, and then j given the observed values of the outcome variable y, auxiliary variables v, and sample selection probabilities, and also given the unknown parameters, have normal distribution with zero mean and the variance sigma, where the entries of this matrix depend on the parameters gamma. We show how this matrix can be calculated. In order to calculate the entries of this matrix, we use the assumption that the sample mechanism is probability is proportional to size, and then we obtain an explicit form of this matrix. And now we can define the likelihood for J based on the normal model, and then we can impose flat priors. Since if we don't have an informative prior, we can impose normal flat prior, and then utilize the Bayesian analysis and apply the full Bayesian significance test. Here is the method. In brief, here I would like to show you the simulation study. We generated 500 populations. For each population, we selected sample of size 50 using the model, which includes y square, which implies that the sampling scheme is informative. And the main goal of the experiments that we carried out was to identify the model holding for the sample selection process. Here we used 3 tests in order, and we calculated for each test, we calculated the evidence value. And here we summarize the results. We applied along with the full Bayesian significance test, we applied the likelihood ratio test and other test which was proposed in the literature. For the first experiment, the power of all tests, in the first experiment we actually tested the informative model, non-informative model against informative model, and actually the large powers of the tests implies that the informative model is more appropriate than non-informative model. And this experiment actually reveals that the sampling mechanism was indeed informative. In the second experiment, both models were not correct, and the tests presented here had very low evidence against the hypothesis. Here, I would like to show one more time. The second experiment, we tested both models are informative, but none of them is true. We utilized the model with y² only, and here actually the results obtained, the obtained results implies that the model with y is more appropriate than the model which contains both y and y². In the third experiment, non-informative model against the true model, and again the powers of all tests were very high, with the highest power for the full Bayesian significance test. I don't have time. See? Don't. Okay. Thank you.